Hello, and welcome back to Introduction to Genetics and Evolution. Now, what we've been trying to do in the last couple of videos is quantify, when you're looking at variation in some traits, such as human height, how much of the variation you see is genetic and how much of the variation you see is environmental. Now, in the previous video, we estimated heritability, or that fraction of the overall phenotypic variation that is genetic, using an F2 cross. Here's the formula, by the way, for heritability. It's, again, that fraction of the overall phenotypic variation that is genetic. Okay? We estimate using an F2 cross. And we started off with tall parents that are all genetically identical to each other. So the genetic variance here is equal to 0. We cross them to short parents that are all genetically identical to each other. So within this box, genetic variance is 0. We got intermediates, the offspring here, from them. The genetic variation within these is also 0. They may be heterozygous for a lot of loci, but they're all heterozygous for the same loci in exactly the same way. Okay, so this is the F1s. From these, we got the F2s. In the F2s, we see quite a bit more spread than we saw in the F1s or in the parents. The reason we see more spread is because we've added this. Instead of VP just being VE, VP here is VE plus VG. We've added genetic variance here. From this, by comparing assuming that this VE is the same as this VE, comparing the two VGs, we can get an estimate of heritability, as you saw. This is not very useful in the context of something like, for example, human height, because we don't have a bunch of people who are all genetically identical that are tall, that we can cross to a bunch of people that are all genetically identical that are short, and look at the offspring and then their grandkids. That obviously is not feasible. Instead, another way to estimate heritability is to use what we refer to as parent-offspring correlation. If we assume that all variation is genetic, and let's assume there's no dominance in this case, then any individual should have exact average phenotype of the two parents. So here's a picture of me. Here's a picture of my wife. If you put us together into some online form, it predicted this is what our kid should look like. This is some sort of intermediate between me and my wife. In contrast, my actual son looks like this. Here's a picture of him. Close to, but not exactly identical to this exact average. Now, oh yeah, he's not usually quite that tan, but he was out in the sun a little bit much that summer. Now, if we look at lots of individuals, we can assess how well the average of the parents' traits predicts the average of the offspring. And then we can use that. We can look at the strength of the correlation, or in this case, the slope of the line, to estimate heritability. So let's imagine a hypothetical thing. Let's take an average height of two parents, and let's say the average height of two parents was 6'0". So let's take another average height of parents and say their average height was 5'0". If the kids, on average, have exactly the same height as the parents, the average of the kids matches the average of the parents. That slope is 1, and therefore the heritability is 1. That is a strong genetic component. In contrast, let's imagine that you see something looking more like this. So you look at the correlation between these two, between the height of the parents and the height of the kids, and you see that in general there's no particular prediction whatsoever. The slope of this line is 0, therefore there is no prediction from the average of the parents to the average height of the kids. This would suggest there's no genetic. Well, we can use this to assess heritability. So I have here 4 figures. In figure A here, this is a case where heritability would be approximately 0, where you have short versus tall, the average for the parents, short versus tall, the average for the offspring, and you see the slope there is basically 0. B, you see some relationship. This would be a case where the heritability is about 0.5. C, here you have a very strong relationship there. The heritability is very, very close to 1. In this case, the height of the parents, the average of the two parents, very well predicts the average height of the offspring. And here's some real data over here. This is looking at students and their parents. This is from the evolutionary analysis textbook. You see the mid-parent height is very close to the mid-offspring height. The slope there is 0.84, suggesting a very strong genetic component to human height in this case. Now that's interesting, but I have to remind you why this matters. Again, there's medical relevance to this. Let's say your parents get gallstones. Is it worth it for you to alter your diet? Right? Or is this predominantly genetic? Do you as a doctor want to tell somebody, no, give up eating meat completely, when in fact, giving up eating meat may have no effect whatsoever on their likelihood of having some sort of disease? No, you need to be able to identify something that's having a strong genetic component versus a very weak genetic component and more of an environmental effect, so you can practice medicine properly. Similarly, let's say you want to breed a friendlier guinea pig. How much will selective breeding matter? Or is friendliness just how much you handle the guinea pig? Something along those lines. Unfortunately, things aren't always as straightforward as I said. Now, everything we've been talking about ignores the fact that parents and offspring may share some environmental factors as well as genetic factors. There's probably a correlation in food availability and other characteristics between parents and offspring. And what this does is this biases upward the estimate of heritability, because we're assuming anything that's shared in this way is from genetics, but in fact there may be some environmental effect that's shared, especially in this sort of parent-offspring correlation as I talked about. There are other assumptions as well. First, that we're assuming the environment is constant, such as, for example, in that F1, F2 cross we looked at. We assumed that VE was exactly the same in the F1 as in the F2. But in fact, the environment is probably not constant. Estimates of heritability may also be very different if you go to different places because VE may be very different. This is also true at different times. And finally, the amount of genetic variation is also not constant in different families or populations. So let's say, for example, that you study in Australia the heritability of human height. That result may not apply if you went to India or if you went to Japan, things like that. Because the amount of genetic variation is going to be different. The amount of environmental variation may also be different. But despite all this, it's not perfect, but it's a starting point. And it's still useful under particular circumstances. So next class, we'll actually go into another means for estimating heritability, and that is what's referred to as the breeder's equation. We'll also talk a fair bit about population growth. That'll be a little bit of an aside. Thank you, and I hope you'll join us.